But then that's not very susceptible, or it's not very resilient to noise. So if you have just one of those transitions gets confused by the reader, then it's going to misinterpret a bit, which has motivated the Miller encoding, so Miller 2 and Miller 4, for instance, and the WISP uses Miller 4. And the idea here is that the link frequency is the same, but there's more transitions per bit. So for instance, Miller 4, there's now 4 times as many transitions, so it's more resistant to noise, but now your data rate actually went down. So with the WISP using 256 kilohertz uplink and Miller 4 encoding, if I do my math right, then it's 56 kilobits on the uplink. So that's the PHY layer. So now on to the MAC layer, which I think somebody had asked questions about before. So the basic way that this works, so the RFID readers, the tags can't hear each other, so they can't take care of their own collision avoidance. So all the collision avoidance has to be controlled from the reader. So the protocol is based on actually a very old networking protocol, which is slotted aloha. So the idea is that the reader first sends a query command, and in the query command it indicates how many slots are going to be in the next frame. So when the readers interpret this query, they then randomly choose one slot out of however many the reader specified. And if one of the tags chooses slot 0, it immediately transmits a random 16-bit number. So in this case, the tag in the top shows slot 0, so it transmitted a random number. And the tag on the bottom shows slot 1 in this example, so it remains quiet. So when the reader gets the RN16, it then sends an acknowledgement, which in this ACK, it contains the RN16. So the tag can receive that and say, oh, okay, well, that's the RN16 I sent, so now I'm supposed to talk again. So now what the tag does is send its identifier. So at this point, that tag has been read. So the reader sends what's referred to as a query repeat. So what this does is kind of steps all the other tags through into the next slot. This indicates, okay, I'm done with slot 0, let's move on to slot 1. So it has 2 effects. The first effect is whatever tag just sent its identifier will now be quiet for the next round. So this way you have a number of collisions. Some of the tags are read, some of the tags aren't read. But then another query will happen, and the tags that were read in the previous round will be quiet now, so there's fewer. And after a number of query rounds, all the tags will be read. So the second effect of the query, along with telling that tag to be quiet, is now the other tags all decrement their slot counters. So in this example, second tag was slot 1, now it's slot 0, sends its RN16, and this process goes through for that tag. Right, so as they're randomly choosing their slots, you're going to end up with some number of collisions. And this is fundamental to the protocol. This is actually good. This is how it works. So in any given slot, you can have 0 tags, 1 tag, or multiple tag responses. And a tag can only be read when there's only a single tag that responds. So in this case, there's a collision. So then the reader will actually go through the remainder of those slots. Some will have 1 tag, some will have 0. And then at the end of that, it will send another query specifying another set of slots. And these tags, again, now they choose another random slot to respond in. In this case, they respond in different slots. So then the acknowledgement gets sent. Now the ID gets sent. So the other thing that can happen is due to noise or some other environmental effects, the identifier the tag sends can get garbled. So that tag hasn't been successfully read. So instead of sending the query repeat, which tells that tag to be quiet, it sends what's called a NAC, which says, okay, you haven't actually been read, but so now just take part in the next round again. Yeah, and those are the details of how, in general, the Gen 2 MAC works. Now, the WISP doesn't actually implement all of that. So some of the implementation details is first, all of this modulation, all the demodulation is implemented in software. The nice part about this is it's really highly flexible. For instance, these WISPs I think used to be Gen 1 WISPs for a previous protocol. When Gen 2 came out, we rewrote the firmware, and now we have Gen 2 WISP, which gives you a lot of power as far as what protocols you can support. But then it has high energy costs because you have to be active while you're decoding all of these messages. And as I kind of mentioned, the WISP supports it supports all downlink rates just because of the way that the software is written. It can actually decode the bits from the reader no matter what downlink rate the reader is using. But the uplink rate is fixed to 256 kilohertz with Miller 4 encoding. The reason for this is that code for transmitting is really tightly optimized from Dan, if I recall correctly, which is a little bit difficult because you have these very tight timing requirements. So if the WISP doesn't respond quickly enough to a reader command, the reader will just ignore it entirely. So this transmitting code has to be hand optimized. So if we've had some people looking to use different readers other than the impinge that have different uplink parameters, so it's definitely possible. And Dan can maybe help you, and I can definitely give some pointers. But what is really going to involve is hand optimizing code for a different uplink rate. So as far as the Gen 2 commands, the WISP actually does decode every Gen 2 command. So there's functions in there that say, oh, if the bits are this, then execute this function because I just got a query command. Or I got a query repeat command. But since everything's in software, every single command you decode costs energy. So if you go through this whole Gen 2 protocol of, choosing a different slot, you then have to decode every one of those query repeats to get to your slot. And then if you have a collision, you now have to wait and take part in the next round. So all of this consumes a lot of energy. So by default, what the WISP does is actually if it wakes up, the next query it gets, it will send its RN16, or if it gets a query repeat, it will send its RN16. Basically, the next opportunity that it gets to send its random number back to the reader, so the reader will read its ID, it just takes advantage of that opportunity. Which there was during the Minutes of Madness, the discussion about the read rates. That's why some of the read rates change. Read rates are different because if you're responding to every query, you can have very high read rates. So if you're returning sensor data, Lanson actually talked to this. By default, what we do is return the data in the ID, so we overload some of it. But there's the other way, which is kind of the Gen 2 sanctioned way of doing it, is after you get the ID, the reader will then send, a request RN, which is send me another random 16-bit number. Then the tag will send another 16-bit number. And then finally, the reader will send a read command for some amount of data. And the key here is that can be a large amount of data. And not only can it be a large amount of data, the reader can do it multiple times. So if you want to get just one sensor value off, it's very cheap to do it in the ID. But if you want to get larger amounts of data, it actually costs less energy to do it with the read command because now you can actually read bulk data off. You can continue to read it as rapidly, basically, as the WISP can generate the sensor values. So, in summary, the WISP is based on UHF RFID, and since everything is, right now it works with Gen 2 readers. It doesn't actually implement the full Gen 2 protocol. But what's nice is we can now exploit all of this existing infrastructure. But since everything is in the PHY layer, or everything is in software, you can actually make whatever MAC layer you want, whatever PHY layer. You can get it to work with any reader you want, or implement any of the Gen 2 capabilities, just with some C coding. And then, as I said, the sensor data can either go back in ID, or for larger amounts of data, it can go in the read command. Questions?
What would you like to see
It really depends what you want to do. So later on I've actually implemented the full Gen 2 protocol with all the random number and all the slotting because we wanted to read a lot of tags. So when we weren't using the slotting, if you had one tag very close to the reader, it would respond every time and no one else would get a chance to. But the problem is if you only have one tag, you guys were showing read rates of 160 samples per second or something. We're seeing 40 samples per second. It's because it's more energy intensive to do the whole protocol. So I think a lot of it's going to depend on what your application is and what you're trying to do.
In the back.
I wonder if the number of tags in the range of the reader is increased, what is the setting up time of the communication between reader and tag? Is it like linear increase, or how does it depend on the number of tags?
With a WISP or with standard tags?
WISP.
With a WISP, so a lot of, especially if you're far away, a lot of what's going to dominate is the WISP getting enough energy. Because sometimes it will take, 400 milliseconds for a WISP to get enough energy to respond. So now it's not so much the protocol as much the WISP getting enough energy to respond. And there's also some interesting interplay between the reader and the WISPs. So when the reader isn't seeing any tags, it actually duty cycles between powered up and powered down pretty rapidly. So a lot of the time, the reader is actually powered up. But as soon as it sees one tag, for reasons that I can talk about offline, it begins transmitting more energy. So what you can actually see is if you have one WISP, it doesn't work as well. And as soon as you put two